Yo, what's up everyone? Patrick here, welcome back. And in this video, what we're gonna do is we're gonna show or prove that the square root of 2 is irrational, that it's an irrational number. And before we get into the actual proof, I actually wanna quickly review how numbers in general are categorized because it's gonna be important for this proof. So if you remember numbers, the two highest level categories, they can either be real numbers or imaginary numbers. And root 2, if you notice, is definitely going to be a real number. Remember, real numbers are from negative infinity to positive infinity. Notice that the square root of 2 is going to be some kind of decimal number, which is between negative infinity and positive infinity. Imaginary numbers, if you remember, they contain that imaginary unit I, the square root of -1, and notice we're not dealing with that when we're dealing with root 2. So root 2 is definitely going to be a real number, and if you remember, real numbers can be one of two things. They could either be a rational number or an irrational number. So when we have to prove that root 2 is irrational, we can go about it in one of two ways. We can prove directly, we could try to prove directly that it's irrational, or we can go about it in an indirect way, and we can show that it's not rational. Because we know that root 2 is a real number, and so if a real number is just one of these two categories, if we can show that it's not rational, then indirectly we prove that it's irrational. And that's what we're going to do in this proof. We're going to go about it in the indirect way. We're going to show that it can't be rational, and therefore it has to be irrational. So it's an indirect proof, or a proof by contradiction. That's another name for it. So what we're going to do is, to start off, is we're actually going to assume that the square root of 2 is rational. That's going to be our initial assumption. And then if we could show that this assumption is incorrect, that it can't be rational, then it's going to be irrational. Now, if the square root of 2 is rational, if you remember, a rational number can be written as a fraction of integers, right? Where this m and this n are integers, where n can't be 0. And another thing is m over n here, we're going to assume that this is in lowest terms, right? So that this fraction is irreducible. Or another way to state that is m and n have no common factors besides 1. But we don't really include that because you can always divide everything by 1. That's going to be a factor for everything. But other than 1, there's no common factors for m and n. So for example, if you have like 2 over 3, notice there's no common factors between 2 and 3. So this is in lowest terms. It's irreducible. But if you have something like, let's say, 4 over 12, well, notice that a common factor for both of these is 4. So we could divide this by 4, divide this by 4. And we would end up with 1 over 3, right? And then 1 over 3, 1 and 3 have no common factors besides 1. Another way to state this is that m and n, if they have no common factors besides 1, is their coprime, right? So there's different ways to state this. I'm going to state it like this, that m and n have no common factors, so m over n here is in lowest terms. And so what I'm going to do from here is I'm actually going to work with this. And to start off this, notice this is an equation here. What I'm going to do is I'm going to square both sides. So what we do to one side, we got to do to the other. And so notice that the next line here would be 2, the square root of 2 squared is just 2, equals m over n squared, the numerator gets squared, and the denominator gets squared. So we'll have 2 equals m squared over n squared. Now, kind of want to show a relationship here between m and n, and then m squared, and then n squared. Now remember, m and n can be any integers as long as n is not 0. So let's write some examples down here. Let's do 1, 2, 3, 4, 5, 6. Right, just a couple of examples. These integers, they could be negative. M can also be 0. The top can be 0, but I'm just going to use these 6 examples. So if m or n is these 6 examples, well then m squared or n squared, if we square these numbers, what we'll end up getting is 1, 4, 9, 16, 25, 36. And so the reason why I wanted to write this down is notice that if m and n are integers, as we've stated, then notice that m squared or n squared are going to be integers as well. So I want to write that down over here. So m squared, n squared are integers. They're actually not just integers, they're also perfect square integers, meaning that when we square root them, these values will end up with an integer. Remember, the square root of an integer will either give you an integer or an irrational number. But if it's a perfect square integer, then the square root of that perfect square integer will give you an integer. So m squared and n squared, they're not just integers, they're also perfect square integers. And so stating that's going to be important for the proof, because what we're going to do now is we're going to rearrange this equation. This 2 here, I'm going to put over 1, and then I'm going to cross multiply. So notice that what we'll have is 2n squared equals m squared, like that. And this is interesting here because this 2, what it does is it makes both of these sides even. Because just in general, 2 times any integer, which that's what n squared is, it's definitely an integer. 2 times any integer, what's that going to give you? It's going to give you an even integer, always. So notice if we take this 1, if we multiply by 2, we'll get 2. If we take 2 multiplied by 2, 4, 6, 8, 10, 12. If we take any negative integer multiplied by 2, that will give us an even integer, right? So 2 times any integer will always give us an even integer. And so notice that what we're doing here is we're taking 2 and multiplying it by an integer. N squared is an integer, so we know that this left side is going to be even. Well, that means that this right side is also going to be even, right? Both of these are equal. And so what this tells us here is that m squared, it's not just a perfect square integer, it's an m squared is an even perfect, you know what, I'm just going to erase this, give myself some room here. So m squared is an even perfect square integer. Right? So we just added this new characteristic to m squared. Before m squared, we knew it has to be a perfect square integer. Well, now because of this here, 2 times an integer gives us an even integer. So m squared is an even perfect square integer. And that's interesting because what that means is that if you notice, the m has to be even then as well. Because if we go through these are all perfect square integers, which ones are going to be even? Well, notice the 4 is even, the 16 is even, the 36 is even. The others are odd. So notice when we square root an even perfect square integer, what do we end up with? We end up with an even integer. Notice 2, 4, 6, right? The next one would be, if we had 7 and then 49, notice 49 is odd, so the square root of 49 would give us 7. But then notice that the square root of 64 would give us 8. 64 is even. It's an even perfect square integer. The square root of that is going to be even as well. So notice that pattern is always going to hold. So if m squared is an even perfect square integer, what that means is that m is an even integer. Right, just from that pattern that we just showed. So what I'm going to do is I'm actually going to take this here and I'm going to write it up here. Just keep the flow going. So m is an even integer. Now, we know, as we stated before, 2 times any integer gives us an even integer. So what we can actually do is we could take m and we can write it as 2 times some kind of integer. Let's call it k. So let's say k is an integer. Not necessarily an even integer, but it is an integer, right? Because as we stated before, as we showed, 2 times an integer is an even integer. So what we're going to do is we're going to take m, that even integer, and state it as 2 times k, where k is some kind of integer. And so what we can do then is we could take this expression and plug it in here. So what we'll have is 2n squared equals 2k squared, like that. And this is interesting because now what's going to happen is if we simplify this, we'll have 2n squared equals now 2k squared. Notice these are 2 are multiplying and then we have an exponent. So we could take the 2 to the power 2, which would be 4, and then k to the power of 2. And then what we can do from here is we could divide both sides by 2, and we would end up with n squared equals 2k squared, like that. And what happens here now is we stated that k is an integer, so we know k squared is an integer. In fact, it's going to be a perfect square integer, but I'll just write integer here. So k squared is an integer, and we know that 2 times an integer gives us an even integer. So notice how this is going to be even, which means that n squared is going to be even as well. So from here, n squared is an even perfect square integer, just like m squared was. And as we showed, if you have an even perfect square integer, well then the square root of that is going to be even as well. So from this, as we showed for m squared, that means n is an even integer. And at this point, we're actually done the proof. Why is that? Well, if m, we showed m is an even integer, and then we showed n is an even integer. But we assume that m and n have no common factors at the beginning, right? When we said that, when we assumed root 2 is rational, which means root 2 is m over n, where m and n are integers and they have no common factors. This was in lowest form. It was irreducible. But with this here, we just showed that m has to be an even integer and n is an even integer, which means the conclusion from here is that m and n have a common factor of 2, which breaks our initial assumption of m and n having no common factors. And so because we just showed this, we also just showed that root 2 can't be written in that m over n format. And so we just showed that root 2 can't be rational. And if you remember at the beginning, Root 2 is a real number, and so if it can't be rational, then that means the square root of 2 is irrational. And we're done the proof. So we went about it in an indirect way by contradiction. So instead of proving directly that it's irrational, we just showed here that it can't be rational, right? One more time, because m is even and n is even, which breaks that initial assumption that m and n have no common factors, but if they're both even, then they both do have a common factor of 2, which means square root of 2 can't be rational, and so we prove that root 2 is irrational.